Hi everybody, welcome back. This example 3, is yet another example of our relative motion. And it's going to be one where we're going to need to kind of change the subscripts around a little bit of our objects. We've got a husband who wants to go up an escalator at a 45-degree angle, and a wife that wants to go down an escalator to a lower floor at a 45-degree angle. The question that the problem is asking is, what is the husband's velocity relative to his wife? So from her vantage point, what is he actually doing? So I thought it might be helpful, before we actually get into the math of this, if I created a little animation. And so I'm going to show that to you real quick. It's about a minute long. And hopefully that can help us visualize this, and then we can come back here and do the math and solve the problem. Okay? So here we go. Okay, so in this example, we have a couple that is at a mall. I think the problem says that they're a husband and wife, although it wouldn't make sense for them to be at a wedding registry because they're already married, but well, we'll just call them, maybe they're shopping for somebody else. Anyway, they started the wedding registry on the second floor, all right? And the wife wants to go down to the first floor, so she'll go down a 45-degree escalator to the first floor, to the linens, and the husband is naturally going to want to go upstairs to check out the power tools. All right, so let's see if this animation can sort of clear up what their motion is going to be with respect to each other. So here, the wife goes to the escalator, approaches the escalator, as does the husband. All right, so they're basically shoulder to shoulder. Now, how are they going to move with respect to each other? They're both going to move towards the right, but he's going to be moving up and he's going to be moving down. So let's look at them and see how they move with reference to each other. Well, they're both moving to the right, but he's moving up and she's moving down. So it's kind of like he winds up being directly over her head, almost as if he shot straight up 2 floors over her head. Let's check that out one more time. All right, so he's moving straight up in the air. So from her vantage point, it's like he's shooting straight up like a rocket ship. All right. The other way to think about it is like this. Let's put everybody back where they originally were. All right. What if the husband and wife reference point, you might say the husband and wife reference frame, were stationary, and we made everything else move? What if the escalators and the floors and everything moved, and we kept the husband and wife where they are? What's that going to look like? It's going to look like that. They're not moving across the screen. They're staying where they are, at least on the x-axis. But since the escalator, either up or down, is moving, as is the ground, we can see that, yeah, it definitely does look like the husband is shooting straight up in the air, almost like a rocket. All right, so the problem that is this example that we're going to try to show is, let's prove that from the wife's vantage point, the husband does actually appear to move straight up overhead. That's what the question of this problem is going to be, and I think by the end we'll be able to go ahead and prove that. All right, so does everybody have the premise here? So let's go back to our problem, and let's apply some values to this. First of all, we need to establish our 3 different points of reference. We have our husband, right there at the top right there. We'll call him 1. We have the wife, 2, and we have the ground, or the floor, that'll be 3. Okay? In fact, I should probably change that around a little bit. I shouldn't call them 1, 2, and 3. Well, those are our 3 different things. H is for husband, sorry. G is for ground, or the floor, or anything else that is not moving. And W is for wife. Okay, and so this is going to be important because these are our 3 different frames of reference. So the husband is moving up, all right? We're going to give him a red vector right here. And it just says V husband. Well, V husband with respect to what? Well, he's moving up with respect to the ground. So we should really call it the velocity of the husband to the ground. All right? Even if the wife wasn't with him, If it was just the husband and the ground, then from the ground's vantage point, the husband would appear to be moving up in the air, like that, okay? Likewise, and I'll make this one blue, all right? The wife is moving in this direction. We call it the velocity of the wife, but not just the velocity of the wife, but the velocity of the wife with respect to the ground. All right? And by the way, each of those has a value. The husband with respect to the ground is what? How fast do the escalators move? They move at 2 meters per second. All right, so the husband is 2, it's kind of a small 2, isn't it? 2 meters per second at what angle? That's going to be at 45 degrees north of east. Okay? Likewise, the wife is going to be moving at the same rate of speed, 2 meters per second, but this is going to be at 45 degrees south of east. Okay, so what the question is asking is, how is the husband moving with respect to the wife? That is, from the wife's vantage point, what is the husband doing? Well, we saw in that animation that it's going to look like that he's going to be shooting up directly over her head. Well, we're going to prove this now, okay? So the question is, and let's make this purple, what's the velocity of the husband, oops, not to the ground, we did that already, with respect to the wife. Husband with respect to the wife. That's saying, from the wife's vantage point, let's pretend that maybe, think of her as being stationary. What's the husband doing? Well, we're going to find that he's going to be shooting directly up. But we've got a problem right here. Because, remember, our format has to be the velocity of 1 to 3 equals the velocity of 1 to 2 plus the velocity of 2 to 3. Okay? 1 to 2 plus 2 to 3 equals 1 to 3. Well, our 1 to 3 is the husband to the wife, all right? Velocity of the husband, I'm not drawing that very well, am I? Husband to the wife. So we can think of that as 1 to 3. The problem is this. We have husband to the ground, right? So velocity of the husband to the ground. That seems to make sense because if husband is number 1, then that H right there matches up with the number 1. But the problem is when we write down the velocity of the wife to the ground. So this is going to be blue plus the velocity of the wife to the ground. Well, if right here, if object number 3 is the wife, then that's not matching up very well because it's saying the wife is 2 and the ground is 3. Well, we want the ground to be 2 and the wife to be 3. So what should we do? What do we need to do right here? We need to change this. We need to change the direction of this. So you can think of it like this. The wife is moving down this way towards the ground. Or you can think of it as the ground is moving upwards that way in the opposite direction towards the wife. Think about it. If you go down an escalator, things seem to move and come up at you. Well, we need to flip this around. We need to make this the velocity of the ground to the wife. Then and only then does it match the 1 to 2 plus 2 to 3 equals 1 to 3. All right? Husband is 1, ground is 2. Ground is 2, wife is 3. And so therefore we can add this together and this together to get the velocity of the husband to the wife. The only thing is that we need to remember that in order, and we can do this, we can change the order of the subscripts. We just need to make sure that we remember that the direction is changed. So instead of the wife going down the escalator at 45 degrees south of east, we can say the velocity of the ground to the wife is going to be 2 meters per second at 45 degrees. The escalator the ground is moving up that way. That's going to be north of west. North of west. And that's what we're going to have to use when we add that to our velocity of a husband to ground to get the velocity of the husband to the wife. Okay? So let's set up our vector addition table using components. All right, and we can just add husband to ground plus ground to wife to get husband to wife. So I'm going to write this sort of in the middle right here. Vector, magnitude, our direction theta, the x component, and the y component. All right? Kind of cram that in there like that. I think I'll try to save some space for our final values. All right, so we're trying to get the velocity of the husband from the vantage point of the wife, or with respect to the wife, okay? We have the velocity of the husband to the ground, right there. And we also have the velocity of the ground to the wife that we're adding, right? We're adding it in that order, the velocity of the ground to the wife. So that's 1 to 2 plus 2 to 3 is going to give us 1 to 3, the velocity of the husband to the wife. All right, let's write in our values, get our x and y components, add them together, and then we should be just about done. Husband to the ground, he's moving at 2 meters per second, right? The angle is 45 degrees, and that's north of east, right? The ground to the wife. Remember, the wife is moving down towards the ground, like so, but the ground is moving up towards the wife, so it's going to be 45 degrees north of west. So it is also 2 meters per second, 45 degrees, but it's that way. The ground is moving up towards the wife. All right, let's get our x and y components. Remember, x is a magnitude times the cosine of theta, and y is magnitude times the sine of theta. So let's get our x. So the magnitude is 2 times the cosine of 45 degrees. That's 1.4. All right, and 2 sine of theta is going to be, lo and behold, the same thing, 1.4. All right, let's ask ourselves, are there any negatives here? No, we've got a positive x and a positive y, so they both stay positive, but I think things are going to change with the ground to the wife. Well, I think if we use a little bit of a logic right here, we're going to find with the same magnitude and the same direction, we're going to get the same values. 1.4, magnitude cosine theta, and magnitude sine theta, 1.4. The only difference is, look, we've got a negative x value. This is pointing in the negative x direction, but positive y. So that means we have to put that negative sign in front of the 1.4 right there. Okay? All right, let's go up and add up our x and y components and see what we get for components for our resultant vector velocity of the husband of the wife. Well, 1.4 plus 1.4 equals 2.8. Okay? And 1.4 minus 1.4 is 0. So we're going to find that there's no x component of their motion with respect to each other. All we need to do now is find the magnitude and the direction, and that'll solve our problem. All right. So the magnitude. I'm going to write it down below just because it probably makes a little more sense. What's the magnitude of the velocity of the husband to the wife? Well, that's going to be the square root, we're using our Pythagorean, of 0 squared, that's easy, plus 2.8 squared. All right? Well, we probably shouldn't need a calculator to figure that out. That's just going to be 2.8. 2.8 meters per second. Well, what's the angle going to be? Well, that shouldn't be hard to figure out either. Our theta, I am going to use this right here. We can see that there's only a y component, 2.8. There's no x component, so it's going to be straight up. But to prove it, we can take our inverse tangent of 2.8 over 0. And I just realized what I just said. You can't divide by 0, can you? It's going to be undefined. So what that means is you have a vertical line. There is no slope. And so the line is straight up in the air. That is, it's 90 degrees. Oops, I'm trying to write with my laser. 90 degrees due north. All right? So that's our magnitude. That's our direction. And that shows that the husband is going to shoot straight up over the wife's head, as it were, at least from her vantage point, because he's moving straight up in the y direction. She's moving down, but they're both moving kind of in sequence, or they're both kind of synchronized in the x direction. But they're very not synchronized in the y direction, because he's shooting straight up, but apparently from her vantage point right overhead. All right? So that's example 3 in our relative motion chapter. Make sure you contact me if you have any questions. In the meantime, thanks for following along, and I'll see you on the next one.